So imagine you're trapped by an evil scientist who wants to investigate how strong of an electric field the human body can take. He trapped you inside a metal cage and now applies a huge electric field between his two capacitor plates. Amazingly, you don't feel any difference. You're completely fine. But how is that possible? The answer is that there is actually no field at all inside your cage. With no field inside the cage, there was nothing to harm you. The reason for why there was no field is a very important property of electrons inside a conductor, which is that some electrons are free to move around inside a conductor. Remember that your cage is made of metal, a conductor. When the scientist applied that field, here's roughly what happened. At first, there was a field inside your cage. Because of that field, electrons started moving along the field lines to one edge. But because they can't leave the metal, they started piling up on one side of the cage, accumulating negative charge there. Further, the electrons left behind protons on the opposite side, which created a positive charge over there. Thus, a small electric field started to build up opposite to the applied field. But since the applied field was still dominating, electrons kept moving, steadily increasing the strength of the counterfield until it became just as big as the applied field. At that point, the two fields canceled each other, leaving no net electric field inside. This process happens in any conductor of any shape when you apply an outside electric field to it. It is the reason why there is never an electric field inside a conductor, at least in electrostatics. Back to the evil scientist. You're still trapped in his cage. Dissatisfied by your lack of pain, he brings out his Tesla coil, planning to give you the shock of your life. But when the lightning strikes, nothing inside your cage really changes. You're still completely fine. The reason is once again that electrons are free to move within metals such as the one your cage is made of. Every time you place excess charge on a conductor, that charge will distribute on the surface of the conductor. This occurs because like-charged particles, such as electrons, exert repulsive forces on one another. To achieve the greatest possible separation and minimize their mutual repulsion, these excess charges push each other outwards until they reach the conductor's surface. Unable to leave the metal, they then accumulate there. In fact, this is a general and really important principle. On a conductor, any charge is distributed over the surface of the conductor. Furthermore, the charges distribute over the surface in such a way that there is no electric field inside the conductor. The reasoning for this goes something like this. Say you put 3 extra electrons on a conductor. Further, let's assume that 2 of these, A and B, are fixed in place with C free to move. Electrons A and B exert a force on electron C, which can be broken down into a component parallel and a component normal to the conductor's surface. Electron C is now being pushed around by a net force moving toward the surface. Once there, it can only move parallel to the surface. It continues moving, but it gets further away from electron A and closer to electron B. Electron B exerts a force whose parallel to the surface component is opposite to the one from electron A. Therefore, the component parallel to the surface of the net force on electron C decreases as it moves until it eventually becomes 0. Then, the electron will stop. Now, in reality, none of the 3 electrons would be fixed in place. They would all move. But the exact same thing that happened to electron C in our example will happen to all of them. They keep moving until they reach the surface, and the parallel to the surface component of the E field on them is cancelled. When all the charges stop moving, there can also be no electric field inside the conductor anymore. Otherwise, the electrons would start moving again, reaching new positions where the only component of force on them would be normal to the surface. For an irregularly shaped conductor, the same thing would happen. So that is the reason why you're fine, even when the lightning strikes your cage. All of the incoming charge is distributed on the surface of your cage, therefore it does not reach you. Further, there is also no electric field. So we found that there is never an electric field inside a conductor, at least in electrostatics, and that any excess charge resides on its surface. What I find particularly fascinating about these two properties is that they arise from one very simple idea, which is that some electrons inside a conductor are free to move, and because of this, they move to positions where there are no more forces exerted on them, causing them to stop moving. Now you may wonder why I tell you all of this, if this is, like the title promised, a video on how electricity really works. The reason is that the properties we just discussed are really important for understanding electricity at a deeper level. I promise that we will get back to them later in the video. But for now, I would first of all like to introduce you to the structure of this video. My goal is to explain how electricity works by way of a concept known as the surface charge gradient. Specifically, I would like to offer you insights on questions that daunted me when I first learned about electricity, such as, how does voltage cause current? For a long time, I did not really have any intuition for voltage. I just never fully understood how it worked, and I feel like many do neither. But to me, the surface charge gradient offers a really nice intuition for how voltage causes current. Another question I would like to answer is, why does voltage jump? What I mean by this is that voltage is generally constant throughout a wire, but then all of a sudden jumps from 0 volts to 12 volts at a resistor with no progression. And yet another question I long wondered about was, why is electric current constant throughout a circuit? I think I have answers to these questions, and I would like to present them to you. At first, I'll explain how a battery works. Next, we will consider how excess charge moving into a wire creates a surface charge gradient and what implications this gradient has. After that, we are going to ask ourselves what happens at a resistor. Finally, I will summarize the big ideas of how electricity works, and at last I will make a few more remarks that I think are worth noting. But before we begin, I would like to emphasize that I am still a beginner in physics and electricity. This video is meant as a kind of discovery journalism in which I share the things I learned with you. I am by no means a professional and have no academic degree. That means certain claims I make may be inaccurate or outright wrong. Please keep that in mind and check whether what I am saying is correct or not. If you find some explanation in this video that is wrong or inaccurate, I would love to hear about it in the comment section so that I can learn what I do not understand correctly. But now let's begin by explaining how a battery works. Basically, a battery creates a potential difference. Let's first of all understand what electric potential energy, electric potential, and potential difference mean. Electric potential energy is the energy a charge feels due to its position. As an example, consider an electron next to a large concentration of negative charge at position A. Because the electron is feeling a repulsive force, it takes work to move it to that point. The work done on the electron transfers energy to it. In a sense, the electron receives energy due to its position. That energy gives the electron the potential to move, hence the name electric potential energy. Now let's place the electron at position B, further away from the big charge. It is now feeling less of a repulsive force. Therefore, it has less energy due to its position, or in other words, it has less potential energy. Next, electric potential is the electric potential energy per unit charge. Its unit is the volt, and it is what we generally use to measure how much energy a charged particle has due to its position. You might just think of the electric potential, which I'll refer to as just potential, as the electric potential energy. This is not quite accurate, but saves you some confusion about certain conventions from electrical engineering. If you're curious, however, you can skip to the timestamp on screen for a more rigorous mathematical explanation of potential and then come back here to move on. What is important is that electrons naturally move from low potential to high potential. If that confuses you, skip ahead for the explanation. In our example, location A is at low potential, while location B is at a high potential. Now we can introduce the potential difference. It is simply the difference in electric potential between two locations. There is clearly a potential difference between location A and B, and here is the clue. If we allow the electron at location A to move, it will move to location B and further. It follows the potential difference, because it is being repelled into that direction. A battery uses chemical reactions to build up a potential difference. In the positive terminal, a chemical reaction consumes electrons, leaving behind positive ions, building up a positive charge. In the negative terminal, another chemical reaction produces free electrons. Thus, we now have a positive charge on one side of the battery and a negative charge on the other. The electrons in the negative terminal would love to move to the positive terminal, from low to high potential, but the battery is built such that they can't. There is a barrier. In this manner, the battery has created a potential difference between its two terminals. Before we move on, note that potential difference also has another name: voltage. I prefer to use the term potential difference because it actually tells you what is meant. Going forward, I'll mostly use potential difference, but sometimes refer to it as voltage as well. If you have heard of this definition of voltage, you might have an understanding for what it is. The part that always confused me, and maybe you too, is how it actually causes current. This is what we will move on to now. Consider what happens when the battery is connected to a circuit. The potential difference inside the battery pushes electrons out of the negative terminal into the wire. There are now more electrons inside the wire than usual, so we have excess charge. But what happens to this excess charge? As you might recall from the introduction, those extra electrons should move to the surface of the wire. This indeed happens. They redistribute themselves along the wire's surface. Usually, they would arrange such that there was no net electric field. However, the battery continually pushes new electrons into the wire. Thus, there are always charges moving. We are thus now in electrodynamics, not electrostatics. In this situation, it is not possible for the electrons to arrange such that there is no electric field. This time, the electrons distribute in a different way. They form a constant gradient of surface charges. The word gradient refers to a change in a quantity. In this case, the quantity is the amount of surface charge at a given location on a wire. As you can see in this image, the surface charge gradient really just means that as you go 1 unit of length down the wire, the amount of surface charge changes by the same amount. In this example, per unit length, the amount of surface charge reduces by 1 E-, the charge of the electron. Anytime you have a location A where there is more charge than at another location B, an electric field builds up between those two locations. Since we now have many of such locations, and because the difference in charge from one location to the next is always the same, the surface charge gradient creates a tiny, uniform electric field inside the wire. That homogeneous electric field is the key to understanding electricity. It moves free electrons inside down the wire. In other words, it causes current. We can now take a look at a bigger picture. Everywhere in the circuit, a constant surface charge gradient is formed almost instantly after the battery is turned on. On the wire connecting the negative terminal and the resistor, surface charges are negative. On the wire connecting the positive terminal and the resistor, they are positive. All in all, this whole surface charge gradient produces a uniform electric field everywhere inside the wire. That E field then acts as a motor for current. It also explains why current is constant throughout the wire. The electric field, the motor of current, has the same strength everywhere in the wire. Thus, electrons are being pushed by the same force everywhere. It is therefore that current is constant. But you might still have some questions lingering on the concept of the surface charge gradient, such as, why does the electric field formed by the gradient have to be uniform? This is a particularly insightful question. The answer takes us back to the principle that there can never be any excess charge inside a conductor. What you have to understand is that current is actually the mechanism by which the wire maintains that neutral charge on the inside in the electrodynamic situation. To understand this argument, consider a region inside the wire. Electrons are constantly being pushed through the wire at a somewhat steady pace because current is constant. Because that pace is the same everywhere, as some electrons move out of the region, an equal amount of electrons move in. Thus, if we take snapshots of the region, we will always find, on average, the same amount of electrons inside the region. We never really find a snapshot where there is less or more charge inside the region. So effectively, the region always remains neutral. The mechanism by which this is achieved is the steady current. Because the current is constant everywhere, you could consider any region inside the wire. You would always find it to be on average neutral. Let's now consider a hypothetical scenario in which the surface charge gradient is not constant. Say that in the center of a section of the wire, there is all of a sudden a larger than usual change in the amount of surface charge from one location to the next. In that case, the electric field wouldn't be uniform. It would be stronger near the center. That would accelerate electrons faster near the center. In other words, current would not be constant. Now consider the region in the center of the wire. Because the field is stronger, electrons move faster through it. This leads us to a problem. The average amount of electrons inside the region decreases. In our example, there should be 8 electrons and 8 positive ions in each region of this size. But as we can see, there are now only 4 electrons on average inside the region. However, there are still 8 positive ions, so the region becomes positively charged. But as we have seen in the introduction, there can never be any charge inside a conductor because excess charges move to the surface. So how can this issue be resolved? The answer is that the surface charges rearrange themselves to eliminate the charge inside the wire. To do this, they need to distribute such that current becomes constant, because this, as we have just seen, maintains a neutral charge. And since the motor of current is the electric field has to become uniform for current to be constant. Therefore, the surface charges have to arrange in such a way that the E field is uniform. To summarize the answer to the question why the E field has to be uniform, we could say that if the field was not uniform, current would neither be constant. If current is not constant, that means regions inside the wire accumulate charge. That charge will then cause the surface charges to rearrange such that the current and the electric field become uniform, so that the inside of the wire becomes neutrally charged. I think this is a beautiful insight as it shows that the surface charge gradient will always automatically adjust itself in such a way that the E field and thus current are uniform. And what I find even more striking is that all of this just originates from the simple idea that electrons are free to move inside a conductor. So now that we know the basics of the surface charge gradient, we can turn toward resistors and ask how the surface charge gradient behaves there. The resistor is made of a different material than the wire, that is more resistive to electron flow. However, it is still a conductor. If you had the same electric field inside the resistor as in the wire, electrons would move slower through the resistor, because there is more resistivity. That would mean that current would not be constant anymore. But as we've seen, the surface charges always auto-rearrange themselves to maintain constant current. So how does that work in this case? First, consider that the free electrons within the resistor experience more resistance, meaning they cannot move as quickly as in the wire with the same electric field. This effectively builds up a negative charge which blocks the incoming electrons. Thus, electrons would momentarily start to accumulate at the entrance of the resistor. In other words, the region left to the resistor would become negatively charged. To avoid that charge, some of the piled up electrons move to the surface. Because of this, the amount of surface charge at the entrance spikes. Near the exit of the resistor, you could think of hypothetical positive charge carriers moving to the surface, as due to the lack of electrons over there, positive charge accumulates. What this means is that at the resistor, the surface charge gradient actually changes. It gets steeper at the resistor. That steeper gradient produces an electric field inside the resistor that is stronger than the one inside the wire. Electrons are now being pushed faster through the resistor to give space to the new incoming electrons. In this way, the resistivity of the resistor is counteracted by a stronger electric field to maintain a constant current. This stronger electric field is also the reason why most of the energy from the battery is dissipated as heat at the resistor. A stronger electric field is required to drive electrons through the more resistive material at a constant rate. And this continuous work done by the field against the resistance leads to greater energy conversion into heat within the resistor. In comparison, the electric field inside the wire is much weaker than the one at the resistor, which is why very little energy is lost in the wire. From this picture, we can also explain why voltage jumps at the resistor. The stronger electric field inside the resistor continuously does work on the electrons as they move through. The electrons transfer this energy to the material's atoms through collisions, dissipating it as heat. This work done by the electric field against the resistance is what causes a significant drop in electric potential across the resistor, which is just another way of saying that a potential difference, aka voltage, is built up across the resistor. But as we measure the potential at the entrance and exit of the resistor, we see this total change in potential, or voltage drop, all at once. This makes it seem like a sudden jump, when in reality this drop in potential is really a gradual process across the resistor. So to make it clear once again, there is no sudden jump. It's really just that we measure the potential difference across the full resistor. But more importantly, what this shows is that the surface charge gradient really is the mechanism to, in a sense, transport the potential difference from the battery to the resistor. At the resistor, it is used to get the energy for pushing electrons through the resistive material. This is how voltage pushes electrons through the resistor, by causing a stronger electric field. So this is how electricity works. To get an overview of the big picture, let's summarize the big ideas. Probably the most important concept is that in a conductor, some electrons are free to move. Because of this, all excess charge resides on the conductor's surface. Metaphorically speaking, the conductor tries to keep the inside neutrally charged. For this, current must be constant throughout the wire. Thus, when the potential difference inside the battery pushes electrons into the wire, electrons move to the surface to form a constant surface charge gradient that gives rise to a uniform electric field inside the wire. This E field drives electrons through the wire with the same speed everywhere, causing a constant current. The field is uniform because current needs to be constant, and current needs to be constant to keep the inside neutrally charged. This mechanism is how the potential difference from the battery causes electric current. And finally, as we have seen, the surface charge gradient and the electric field auto-regulate themselves at a resistor to keep current constant. To pick up on the metaphor again, electricity, more specifically current flow, is basically the conductor's attempt to keep its inside neutrally charged when charges are constantly moving. What really fascinates me the most is that all of this really originates solely from free electrons auto-regulating the charge inside the conductor by automatically moving to the right positions. At this point, we are almost done with the video. However, I still would like to give some remarks. And some of these are really important, so stick around just briefly. The first remark, which is quite important, is that the animations in this video are technically wrong in one aspect. Electrons generally do not move through wires in straight lines. Rather, they move very chaotically. But because of the electric field, they on average move slightly into one direction. We say that the electrons drift. Drift velocity tells you how much the electrons are moving on average into the direction the E field pushes them to. Usually this drift velocity inside a wire is around 1 millimeter per second, so they move really slow. This also explains why electrons are moving at a steady pace. You might expect them to keep accelerating because due to the E field, there is a constant force on them. However, they are constantly colliding with the lattice, which slows them down, causing them to drift with a somewhat constant velocity. To understand this idea better, I strongly suggest you watch Veritasium's video on how electricity works, which I'll link to at the end of the video. The second remark is on the definition of electric potential. This time, I would like to define it mathematically and explain the conventions around it. A useful analogy for understanding electric potential is the one of the electric field. The purpose of the electric field is to tell us how a given charge A influences the space surrounding it. More specifically, that influence is how strong of a force a particle with charge Q will feel if placed somewhere near charge A. We can characterize the strength of the force between both charges by calculating the Coulomb force between the two charges. That force describes how the two charges interact. But we're interested in how charge A alone shapes the space around it, independently of a second charge. Thus we take the Coulomb force and we divide it by the magnitude of charge Q. This gives us a quantity that is only dependent on the magnitude of charge A and the distance from this charge. To each point in space, it associates a vector whose magnitude is the relative strength any charged particle would feel if placed at that point. Importantly, by convention, the vectors always point into the direction of the force a positive charge would feel. For this reason, electric field lines point away from positive charges and into negative charges, as positive charges move away from positive charges and toward negative ones. In this way, we have characterized the space surrounding a charge A by associating a vector to each point in space surrounding it, whose magnitude gives how many newtons of force a charged particle would feel per unit of charge. The reason that the E-field is useful is because it gives us a measure for comparing forces at different locations without having to worry about what charges we use to measure the force. We only have to know the charge of our observed charge A and the distance from it. This will then be sufficient to calculate at which point the influence of charge A on other charges would be stronger. Now, with electric potential, we want to do the exact same as with the E-field. This time, we're looking to characterize the energetic imprint of charge A on the space surrounding it. That is, we would like to find a general measure for how much potential energy each unit of charge receives, to compare different points in space with regard to how much energy they give to charged particles. We can do this analogously to the electric field. In this analogy, the Coulomb force is similar to the electric potential energy U of a test charge Q, and the electric field is similar to the electric potential. What we do is calculate the electric potential energy of a positive test charge Q at a location in space. Next, we simply divide the electric potential energy by the magnitude of our test charge to get a quantity solely dependent on charge A that characterizes the energetic imprint of this charge on this specific location. Then we repeat this process for each location in space. We call this new quantity, which describes how much potential energy per unit charge is associated with a point in space, the electric potential V. Like the electric field, it is used to characterize not an interaction, but rather a property of space. Once again, we have an important convention. The electric potential energy U we use to calculate the electric potential is the one of a tiny positive test charge. This is important because near positive charges, our positive test charge would have a lot of potential energy. And near negative charges, it would have less potential energy because we don't have to do much work to move it near a negative charge. Thus, electric potential takes high values near positive charges and low values near negative charges. But, and this is crucial, electrons would feel the opposite. They would have high potential energy near negative charges and low potential energy near positive charges. However, potential energy is not the same as potential, and we have defined electric potential using a positive charge. This is the reason why electrons move from low to high potential, because when moving from low to high potential, their potential energy actually decreases because the sign of the energy is negative. This convention also explains why, in the image on screen now, the potential is at 0 volts in the wire with negative surface charges, and at 12 volts in the wire with positive surface charges. Hopefully, this helped clear up your confusion about electric potential. If earlier you skipped to here, you may now go back to the timestamp on screen to continue learning how electricity works. With my third remark, I want to emphasize that the E-field generated by the surface charge gradient is really small. This is why we almost never notice it, but it's still sufficient to drive current. Fourth, I did not want to leave you without some idea of how the surface charge gradient would look like if we had two resistors connected in series. I have thought of 3 possible versions which might all work. In these pictures, you can always see that the density of the surface charges is less in the wire connecting the 2 resistors. This will cause the needed electric fields to maintain a steady current. For resistors in parallel, it would probably look like this. But I think if you really understand the concepts introduced in this video, that the specifics of what the surface charge gradient looks like in a given situation are not so important to you. Because in the end, we know that in any case, the surface charge gradient will auto-regulate itself to keep current constant. Thus, we don't really need to know what it looks like. And lastly, the animations provided in this video are not all technically correct. They are meant for illustrative purposes. You should not take them as absolutes for what things really look like. For example, this animation on how the surface charge gradient is formed is obviously an oversimplification. Electrons would not arrange in such big chunks and then move to the surface like this. However, I have chosen to animate it in this way because it nicely illustrates the point that electrons move to the surface to form a surface charge gradient. One last thing is that I would like to acknowledge Veritasium and the engineering mindset. Both of these YouTube channels have made excellent videos on how electricity works, introducing me to the idea of a surface charge gradient and inspiring me to make this video. Their videos have been really useful to understand these concepts. I strongly suggest you check out both of their videos, which at the end I'll link to on screen, to deepen your understanding. I would also like to acknowledge 3Blue1Brown and the Manim community. Manim is the Python library I used to make the animations for this video. 3Blue1Brown has originally created Manim, which some very nice people have then made a community-maintained version of called Manim CE, which I used. Without them, this video would literally not have been possible. Specifically, I would like to thank Benjamin Hackle for his YouTube tutorials on Manim CE, which I'll link to in the description. And lastly, I would also like to acknowledge all the AI tools I made use of for this video and their creators. Google Gemini, ChatGPT, and Sora, from which most of the images in this video come, have been a real help for understanding this topic and making this video. Additionally, the voice you are hearing is actually an AI voice. This voiceover was made using ElevenLabs. With that, I'll end this video here. Thank you so much for watching and have a good day.